This is the last section of our unit here where we talk about something called colligative properties of solutions. Colligative, that word just basically means collections, groups of things. So these are properties of solutions that depend on the number of the particles rather than anything about the identity. So you see this here in this definition. Again, these are properties that are dependent on the concentration of solute, right? So the amount of particles per volume, but it has nothing really to do with the actual identities of the solute. Now, we'll talk about how the identity might have an effect in some other way, but really it comes down just to the number of particles. Three main properties that we will cover are vapor pressure lowering, freezing point depression, and boiling point elevation. There's a fourth one included here, osmotic pressure, which you may remember from your biology contexts of having like the semi-permeable membrane, and then one side has a greater concentration than another, and water can move past. That's actually something we're not going to get into, but that's also one of the potential properties you could discuss based solely on the number of particles that are dissolved in a solution. Let's go and talk about how vapor pressure can be affected by the particles that are dissolved. First of all, remember that vapor pressure is the pressure exerted by the vapor particles of a liquid in a container. And then if you have a lot of vapor pressure, right, that means you have a lot of particles that are up here bouncing around. And those particles, therefore, that would reflect actually the fact that you have weak attractive forces between each of the particles in the liquid phase, because that means that these gaseous particles, the ones that have that are at the surface, are more able to escape and become a vapor. So that means high vapor pressure. Low vapor pressure means that you have fairly strong attractive forces, because that means the attractions between all the particles in the liquid basically keep the particles from being able to escape. And so if you have low vapor pressure, that means you have very few particles that have escaped. Therefore, you can make the conclusion that generally it has strong attractive forces in the liquid phase. Additionally, another term here is a non-volatile solute. If you remember the word volatile, that's a term that refers to how well a particle can escape, how well a particle can go from a liquid to a gas. And so this non-volatile idea is just saying that these are particles that dissolve, but don't itself then become a vapor. So we're basically talking about particles that always stay in the liquid part. So if you imagine, like down in this liquid section here, if you talk about a solute that might be dissolved in it, right, we're not talking about the particles that might escape, right, of the solvent. We're talking about if you add additional particles of something different added in here, those particles don't vaporize themselves. So one of the things that we should know here is that anytime you have particles that are dissolved into a solution, the overall effect is that the vapor pressure of the liquid is lowered. Right? So it's always going to decrease. And basically what that means is that your solvent can't escape as much because you have particles dissolved in it. And what exactly is the nature of that behavior? Well, the vapor pressure, first of all, again, is lowered here as the statement, as I said, just printed out. But it basically says that the attractive forces of your solute, right? So the solute particles that are added to your solvent, those particles are basically exerting some attractive force too, right? They're all sort of all hanging out, and there's some attractions you might imagine, like being between here and here and here and here and such. And so if you have just a pure solvent, you might have some vapor up here, but because these solutes are added, these purple atoms, these substances that are added, again, kind of add to the sort of attractive nature of the particles that are there. So that means the number of particles that can escape is lower. They can't escape as much because these added solutes are doing a little bit more attracting. So generally speaking, we always can identify this as vapor pressure lowering. So what does that mean in terms of comparisons? So let's talk about this really quickly. Let's say you have a solution of 0.100 molar of some solute A, and then you have another solution of 1.00 molar, 0.200 molar of some solution B. Well, again, these two solutions are, sure, made of water and some solute dissolved in them. But the idea is that you have different concentrations of the two substances. So solution A here with a lower concentration versus solution B with a higher concentration, which one of these two do you expect there to be a lower vapor pressure? Which one of these do you expect there to basically attract and hold on to the vapor particles from the water particles from escaping? This one right here, you expect to do a better job of lowering vapor pressure. And so if you're asked the question, which one has a higher vapor pressure, right? Which one of these solutions here, solution A or solution B, which one of these two has a higher vapor pressure? It would be solution A. right? And again, make sure you understand this. Solution B, right? This has more particles dissolved in it, so it can lower the vapor pressure more, right? So it can bring it down more. This solution right here also has particles in it, and it's going to lower the vapor pressure, but won't lower as much as what a solution B does. So we expect that here, solution A is going to have the higher vapor pressure, whereas solution B will have the lower vapor pressure. All right, let's go ahead and take a look at some other contexts here. This is freezing point depression. Freezing point depression is this idea that if you're to dissolve solute into some solution, or to make a solution anyway, it actually takes the solvent and it lowers the freezing point. It drops the freezing point. Again, that word depression basically means dropping. And so this can be represented in a couple ways. Basically, you're going to have some formulas here. You might recognize some of these, but effectively, again, delta TF, this is the freezing point depression. This is the amount that it's lowered by, right, delta TF. This can be calculated in one of two ways. You can either take the freezing point of your solution minus the freezing point of the pure solvent, right? So it's important to identify where your solution is, it's important to identify where your solvent is. You can take these two values and subtract them by each other. Or you can, again, use this other formula. Again, a lot of times these two are used in conjunction with each other. But you have a second opportunity here where it's going to be KF times B times I. All right, so you have a couple things here. First of all, delta TF is that same expression here. That's that freezing point depression. And the freezing point depression can be calculated by taking this molal freezing point constant. All right, this is a value that you'll generally be given, and it has units of degrees Celsius per molal. Oftentimes we'll be using water, so you can use that value of 1.86. B is just sort of a placeholder for the molality of the solution. Make sure you recognize that it's not the molarity of the solution, but molality. And then I is the Van Hoff factor, which represents the number of particles generated by dissolved solute. Now, this is one that you have a lot of experience with when we talk about electrolytes, so that one shouldn't be too hard to put together. All right, let's see how this works and how it's put in action. What's the freezing point depression of a solution where 17.1 grams of sucrose is dissolved into 200 grams of acetic acid? All right, let's be clear about this. We have to identify solute solvents. We're talking about freezing point depression, and that means we have to put all that formula work into action here. All right, first of all, sucrose. This one serves as your solute. Acetic acid, this serves as your solvent. So that means if we're going to do work with freezing point depression, we know that we're going to have to use molality as our formula. So let's go and put that in action. I'll do this real quickly so you guys can kind of get a sense of what to do. All right. First of all, we have grams of sucrose, 17.1 grams of sucrose. Let me go ahead and convert that into moles here for you. Okay, so you go ahead and make the conversion happen. You end up with 0.0500 moles of C12H22O11. Again, just switching the gram amount of sucrose into a mole amount. Now, I also know that I need to use a molality expression here somewhere. Let's go and make that happen. Right, so molality, that's equal to the mole amount of solute over the gram amount of solvent. Let's make that happen here. So here's the molality calculation. One thing I kind of just did on the side here, making sure you convert the gram amount of acetic acid, the solvent, into kilograms, and then toss that into the formula. And then you can do a little bit of math here. Right, then you have 0.250 molal as a result of that calculation. So this right here, again, is not exactly the final answer, but it gets us along the way because it's asking us for the freezing point depression to start. Remember, that's going to be a formula that involves the delta TF, that's equal to KF times M times I, right? M again represents molality. The previous slide probably had a B there, but you can use M in this place perfectly fine. And then let's start plugging some stuff in, right? Because this is a constant we have available to us. This chart right here might be helpful. We do know that M is the molality. We just calculated that, no problem. I is that Van Hoff factor, which talks about the separation of particles. But what do we know about sucrose is that it's considered a non-electrolyte, so we know what that value is. Let's plug those numbers in. All right, so the value here for delta KF, that's going to be coming from here. My acetic acid solvent has a value of negative 3.90. So let's go and jot that in here. This should be negative 3.90 degrees Celsius per molal. Just copying that from here to here. So that, again, is external with the KF value. M, which is molality, that's the thing we just calculated from over here. Toss that in, 0.250 molal times the Van Hoff factor, which is that one we talked about earlier, and do some math. So know that this is going to have infinite sig figs. Go jot that in. Infinite sig figs. This one has 3. This is also infinite because that's a whole number. So you should have 3 sig figs in your final answer. So your value here is negative 3.90 degrees Celsius. That is totally not correct. Let's try that again. That'd be 0.975 degrees Celsius, and that's negative, of course. because the temperature change has gone down. Right? We've decreased that amount. So that takes care of this first question right here, which asks you, what is the freezing point depression? That's negative 9.75. And that makes sense because we dropped the temperature by 0.975 degrees. Now, the other part of this question is, what is the freezing point of this solution? So we've only taken care of part of the problem. This one's asking for the freezing point of the solution. As a reminder, that formula that we saw earlier is that the delta TF, again, is the second formula, is equal to the freezing point of my solution minus the freezing point of the solvent. Right? So let's go and plug some numbers in. The delta TF, I just calculated from right here. That's going to be negative 0.975 degrees Celsius. That's equal to the freezing point of my solution, which again is being asked for. So I'm just going to draw it in freezing point of solution as a parentheses thing minus the freezing point of the solvent. If I look over here, again, how do I get that information? It's provided to me. And that's going to be 16.6 degrees Celsius. That again is what this chart will give me because I wouldn't know the freezing point of acetic acid. Otherwise, that's my solvent. All right, go ahead and solve for your unknown here. That's a freezing point of your solution. And then you'll find that the freezing point of your solution, right, SOL'(N), is going to be what you just calculated. So it's going to be 15.6 degrees Celsius. And that's your final answer for the second part. There we go. So this is basically how the freezing point depression works. There's also some example problems here. You're welcome to try those out, but we'll get to those later on. More importantly, let's go and take a look at this last category of colligative properties. So we've covered the first two, vapor pressure lowering, freezing point depression. The last one's going to be boiling point elevation. Now, as you can imagine, right, this one's going to be very similar to what we saw. We took the freezing point earlier and we put it lower, right? The boiling point now we're going to elevate it. We're going to bring it up. So this is going to be that difference between the boiling point of a solution here and the boiling point of a pure solvent. So this again is the idea where if you take a value of delta T, right, this delta TB, that can be calculated in two ways. Right, this can be either done by the boiling point of my solution minus the boiling point of the pure solvent, very similar to what we did earlier. And then we have delta TB is equal to KB times this B. Once again, that B is basically another way to write molality. So if you want to, you can view this as a script M again, like usual, and then times I, which is that Van Hoff factor. And then you go ahead and put some numbers in together. So once again, you have a combination of two different formulas you can use in conjunction to solve for changes here. So let's try this out. We're actually going to see this very similar problem here. What is the boiling point elevation now of a solution with 17.1 grams of sucrose, surprise, is dissolved in 200 grams of acetic acid? What a surprise, right? It's the exact same solution that we saw earlier, and we're going to measure now, instead of the freezing point depression, the boiling point elevation instead, right? So let's go and put this to action. Let's go and carry over some numbers that we saw previously, including the mole amount. So that'd be 0.0500 moles of sucrose, right, from the previous example, and then also the volume, or excuse me, the mass of my acetic acid. That's going to be 0.200 kilograms of acetic acid, right? And this still serves as my solvent. This still serves as my solute. So again, we're just carrying those numbers over. So once again, you're also going to get the molality. So let's solve for that. Molality is equal to 0.0500 moles over 0.200 kilograms equal to 0.250 molal solution. Okay, let's go ahead and apply that formula that we saw earlier. The question again is asking, what's your boiling point elevation? So we're solving for a delta TB, right? That's the boiling point elevation, the change in temperature according to boiling, the boiling process. And let's plug some numbers in. We're going to have a KB we need to multiply by a molality of the solution times the I of the solution. So what do we have here? KB, again, I don't know that number off the top of my head. Well, that's because we have a nice little chart here that tells us some information. The normal boiling point of acetic acid is 117.9, but that's not the one that's relevant here. We need to find the KB. Here is 3.07. So let's go and plug some numbers in. Delta TB is equal to 3.07 degrees Celsius per molal times the molality, which is 0.250 molal times 1, right? That same Van Hoff factor. Go ahead and plug some numbers in, and you're getting a value. I'm going to squeeze this in here because I planned poorly, so that's 0.768 degrees Celsius of boiling point elevation. That takes care of the first part of the question, which only asks for just the elevation, right? How much does it increase by? So then let's go and finish out the problem where it does ask what is the boiling point of the solution. So once again, reapplying that same formula that we saw earlier. So the boiling point of my solution minus the boiling point of my pure solvent, right? I do have delta TB, which I just solved for. Boiling point solution we're solving for. And then BP, the boiling point of the solvent. Well, I don't know that, but they do tell me in this right here, in this chart. So I can go ahead and plug some numbers in. Let's do this. We have 0.768 degrees Celsius. That's equal to the boiling point of my solution minus 117.9 degrees Celsius. Solve for my boiling point of the solution. That's going to equal to 108.7 degrees Celsius, and that is your other final answer. Alrighty, that'll do it.